Hey everybody, in this video I wanted to go over how to find the limit of a recursive sequence. So the example that we did in class was determining whether the sequence converge or diverge, and I gave you this one, right? A sub 1 is the square root of 6, and a sub n plus 1 is given as the square root of 6 plus the previous term. And so if we look at the notes from Thursday, we can see how we did that. So we found some terms. We found a sub 1, a sub 2, and we calculated them using our calculators and showed that it is going towards 3. So it appears to be bounded by 3. So we introduced the monotone sequence theorem that says if a sequence is monotone increasing and bounded above, then the sequence converges. And if a sequence is monotone decreasing and bounded below, then the sequence converges. So essentially, if the monotone sequence is bounded, it converges. So if it's increasing and bounded above, it converges. If it's decreasing and bounded below, it converges as well. And so we showed how it was increasing, and we showed also how it was bounded. So we show that it is increasing and bounded. So now, how do we find the limit? And so from here, let me just write, by the monotone bounded sequence theorem, our sequence converges. So what does it mean for a sequence to converge? So we can say the limit as n goes to infinity of a sub n is equal to L, right? So that's what it means for a sequence to converge. And L is not infinity. So L is a finite number. All right, so now let's go back to our sequence. We know it's a recursive sequence, so a sub n plus 1 is equal to the square root of 6 plus a sub n, right? So side note here, what do you know about then the limit as n goes to infinity of a sub n plus 1? Well, this means, right, the limit as n goes to infinity equals L means that if you start listing the sequence, right, the first term is root 6, and then root 6 plus root 6, and so on. Eventually, you're going to have plus L, plus L, plus L forever. And so, say this is a sub n, right, the nth term or the kth term, then this is the next term, so that's also L. Right, so then the limit as n goes to infinity of a sub n plus 1 is also L. So this allows us to say, oh, well then, as n goes to infinity, what do we have? A sub n plus 1, right, is going to be L is equal to the square root of 6 plus, as n goes to infinity, we know this converges, so it's L as well. Right, and I'm using this, if a sub n, as n goes to infinity, eventually you look like L, every term after that looks like L. And so now we're going to use algebra to solve for L, the limit. Square both sides. So I'm going to have L squared equals 6 plus L, right? The square root and the square undo each other, and then set it equal to 0. Hopefully it factors. If it doesn't factor, we will use the quadratic formula. But I believe this factors into L minus 3 and L plus 2. Right? Negative 3 times 2 is negative 6, and negative 3 plus 2 is negative 1. And this tells me L is equal to 3, or L is equal to negative 2. Well, we proved before that a sub n is bounded above by 3. So 3 is the upper bound, which happens to then be also the limit. And so the first part of this was we showed that it converged. The monotone bounded theorem told us it converged. Now that we know it converges, that means it has a limit. So we call that L. And now we use this to solve for L, the knowledge of the limit. So therefore, the limit, we can say our sequence and a sub n plus 1 equal to the square root of 6 plus a sub n converges to 3. So that's how you find the limit of, this is a type of recursive sequence. Okay, so hopefully that was helpful. I encourage you to review your notes from class from Thursday to show how did we show that something was bounded and bounded above and increasing in this case. And I used the process of mathematical induction. All right, let me know if you have any questions, and you can ask me also during class any questions on this.